we're going to be talking about something called Maclaurin and Taylor polynomials. This whole first example I'm going to show you is the process of where the thing comes from, and just to give you an idea about it, there is a formula, so just so you know, this first example is more of just an explanation kind of thing. So let's say that we started off with f of x equals e to the x, and e to the x looks kind of like that. So what I want to do is I want to approximate this e to x by a polynomial. And the reason has to do with things not like e to the x, things that are more complicated, where it might be harder to find the derivative or the antiderivative, and you can use these approximations in order to do that. So basically what we're going to do is we're going to start off with approximating it by a line. So basically that's the tangent line, and what has to happen is that the y values are going to be the same and the slopes are going to be the same. So the slope at 0, if I found the derivative of f of x and plug in 0, I get 1. So basically we're going to approximate it with a line, and we're going to call it y equals 1x plus 0. I'm just going to write it backwards for the sake of the problems that we're going to be looking at. Now, if I wanted to approximate it by a quadratic, okay, for the quadratic, I'm going to write this formula a0 plus a1x plus a2x squared. And see, the good thing is that we've already found a0 and a1. So far we know that that is not correct. 0 plus 1x plus a2x squared is the polynomial we're looking for. Alright, so let's start again with e to the x. We're trying to approximate it by the parabola. So basically, not only do we want the first derivatives to be the same, we also want the second derivatives to be the same. So if I found the first and second derivative of this thing, I'll write it here. The first derivative is a1 plus 2a2x. The second derivative would be 2a2. And if I go back to the second derivative of e to the x, I get e to the x, and I know that at 0, this is 1. So if I want the quadratic derivative to equal the e to the x derivative, I would get a2 equals a half. So my quadratic equation would be 0 plus 1x plus 1/2 x squared. Now, we're going to go one step further, and we're going to find the cubic one that would be the same. Again, here's e to the x, and we're trying to approximate it by some cubic function. And the more we do, the closer the polynomial is to approximating whatever the equation represents. So the cubic form would be this form right here. We already know that a0 is 1, a1 is 1, I realize that I'm telling you a0 is 1, and back here I told you that it was 0. This is really a 1. I'm very sorry about that, because the y value at 0 is 1. And so this should also be 1. Again, very sorry about that. So this is also 1. Alright, continuing. A2 is a half. And now we want to find a3. So I'm going to have to find all the derivatives again. The first derivative would be a1 plus 2a2x plus 3a3x squared. The second derivative would be 2a2 plus 6a3x. And the third derivative would be 6a to the third. We want the third derivative of this equation to equal the third derivative of e to the x. Well, the third derivative of e to the x is still e to the x. The derivative is still 1. So we get that a3 equals 1/6. And then, so this here would be the polynomial with 1/6 plugged in. And so what this is saying is that if I wanted to approximate e to the x, I could continue doing this derivative thing and get formulas that represent it. Now, I told you that there's actual formulas here. That was just sort of the process and where it's coming from. The actual formulas are these. Maclaurin polynomials are centered around c equals 0, and its formula is this. And then this pattern continues to the nth derivative over n factorial and then x to the n. A Taylor polynomial is the same thing, except instead of plugging in 0, we plug in c's. So f of c plus f prime of c times x minus c instead of x minus 0, or instead of just an x, plus f double prime of c, x minus c over 2 factorial. I will continue that here. F triple prime of c times x minus c to the third over 3 factorial. Notice all these are the same. And then the pattern would continue to f to the nth derivative of c times x minus c to the n over n factorial. And so the Maclaurin is the first one where it's centered around 0. Taylor is the second one, and it's centered around c. I know it looks complicated, but after you see the process, it really isn't as complicated as it may seem. So I'm going to go back to that first example that we did. We'll call it example 2. F of x equals e to the x. We're going to center it around c equals 0, and we're going to let n equals 4. Alright, and so we're going to do the same problem, except I'm going to show you the process using this formula. So you start off with writing down the derivatives until you get to whatever n is. And it just is kind of long, but it's really not that difficult. So I know all of these derivatives are e to the x. It will not always be that way. Then I evaluate everything at the c value. If I plug in 0 into everything, I get 1. So now I use my formula. It would be starting off with the first value, 1. The second value is 1, you put an x with it. The third value is 1, you put an x squared, and you divide by 2 factorial. The third value is 1, it's x to the third, and then 3 factorial. The fourth value is 1, and then x to the fourth over 4 factorial. You do need to simplify because there are times where you have to come up with a formula, and sometimes coming up with a formula is difficult without simplifying. So you should go ahead and divide, multiply, change factorials or whatever. So the blue is our Maclaurin, because it's c equals 0, Maclaurin approximation for that polynomial with 4 terms, or with n equals 4, meaning the degree is 4. Okay, let's say that we have f of x equals cosine of x, centered around 0, and this time n is 6. That sounds awful, but it really isn't that bad. I do have to find 6 derivatives. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is positive sine, and then cosine, and then negative sine, and then negative cosine. Evaluate each of those at 0. Cosine of 0 is 1. Sine of 0 is 0. Negative 1, sine of 0 is 0. All the signs are going to be 0, cosines are going to be 1s, and then you put the signs. That's the reason it's not that bad, because you get normal numbers. So then the polynomial would be 1 plus 0x minus, using the next term, and then you square it and divide by 2 factorial. The next one would be 0, x to the third, 3 factorial. You just got to memorize the x to the third and 3 factorial. And then plus 1, x to the fourth, 4 factorial. 0, x to the fifth, 5 factorial. Minus 1, x to the sixth, 6 factorial. So if I simplify here, I get 1 minus x squared over 2 plus x to the fourth over 24 minus x to the sixth over 720. Because all these are 0, so they go away. First try problem. Let f of x equal sine of x, c equals 0, and n equals 7. Very similar to that last problem. Alright, let's center it around somewhere else. Let's say that you have f of x equals natural log of 1 minus, x minus 1. And we're going to center it around 2, and n is going to equal 4. Since I'm going to let n equal 4, I've got to find 4 derivatives. Starting with ln of x minus 1, the derivative is 1 over x minus 1. I'm going to rewrite this as x minus 1 to the negative 1 because it will be easier to find the derivatives that way. I'm just continuing to find the derivatives of each one. Alright, we're plugging in 2 now into the derivative. So ln of 2 minus 1 is ln of 1, and I get 0. Okay, plugging in 1 into the next one, 1 minus 1 is, or I'm plugging in 2, sorry. 2 minus 1 is 1 to the negative 1, so I get 1. 2 minus 1 is 1, so everything in parentheses will be 1, so really the coefficients are going to be the derivatives. So now we write our polynomial. 0 plus 1x minus 1x squared over 2 factorial plus 2x to the third over 3 factorial minus 6x to the fourth over 4 factorial. Again, we're going to simplify on this one. It might seem easier, and you know what? I forgot something. Because we're centering it around c equals 2, it can't be an x there. It has to be x minus 2 because we're centering it around that. Alright, so start again. 1 times x minus 2 squared, that's just an x, minus 1 x minus 2 squared over 2 factorial plus 2x minus 2 cubed over 3 factorial minus 6x minus 2 to the fourth over 4 factorial. What I was saying about the simplifying on this one, sometimes you got to come up with a pattern, and there's a pattern here. That's a 2 factorial on the bottom, which is 2, so this is negative 1/2 x minus 2 squared. Alright, 3 factorial is 6. 2 divided by 6 is 3, so there is a 3 on the bottom. Alright, 4 factorial is 24. 6 divided by 24, that's a 4 on the bottom. And see, now I see a pattern. So if I wanted the 5th or the 6th, n equals 5 or 6, it would be easy to find that because I would just do the same pattern that you see. Alright. I've got one more example, but I'm going to give you a try problem before I give you the example. We'll let f of x equals natural log of x. We'll let it center around c equals 1 and let n equals 4. Whenever we do this, it'll have an x minus 1 in it. Okay, last example. Sometimes they don't make you find the derivatives. Sometimes they just say, oh, here's the derivative at 0. Here's the derivative at negative 3. Here's the second derivative, which is 1. And here's the third derivative, which is 4. And it might say, write the third degree Maclaurin polynomial around 0. This one's actually much easier because I don't have to find all the derivatives, but I just wanted to show you that it might not be, there might be problems like that. So you start with the 5, you put the x with 3, go to the 1, it's x squared over 2 factorial. Go to the 4, it's x to the third over 3 factorial. So if I simplify, there may not be a pattern, but I should always simplify just to make sure. That's 4 over 6, so that's 2/3 x to the third, or 2x to the third over 3. So you might not have to find derivatives, it might give them to you.